Lesson 28, activities. In the last problem from the demo, we used our linear approximation to estimate square root of 2. Was our estimate for square root of 2 an over or underestimate? So I'd like us to know based on the graph here. So in this case, the tangent line is always above the curve. So every time we use the tangent line to approximate y values on the curve, we are getting over estimates. So every single one of our answers is going to be an over estimate. In the next question, if a function is concave up, that means it either looks like this or like this. And in both cases, every single tangent line is below the curve. And so if you're using the tangent line to approximate a point on the flat curve, then every single tangent line is going to underestimate. So if your function is concave up, the linear approximation underestimates. If your function is concave down, like in our square root of 1 plus x example, then the linear approximation overestimates the function. Okay, based on the picture, the one on the previous page, give an approximate interval for which the tangent line is a, quote, good approximation for f of x. So I guess really what we're saying is, like, if you look at the curve and at the tangent line, let's take a look and see where we really can't tell them apart. So this is just a ballpark kind of thing. I mean, I can still see them apart, like here versus down here, and I guess probably right around there is the first spot where where the two of them look like they kind of merge together. So maybe x equals negative 0.3, and then maybe right around here is where they start to pull apart. Of course, if we zoom in, then the answer would change, but we'll say like negative 0.3 to 0.5, something like that. It's okay to have slightly different answers than this one. Okay, so you can read the next bit of text. I'm going to jump to number 4, so pause here and read. But let's go ahead and do number 4. So we start with the square root of 1 plus x, which again we'll write as 1 plus x to the half. Let's do this first column, f prime of x. We did this one in the demo. And then f double prime of x, the negative 1/2 comes down, giving me negative 1/4 when I multiply. Copy this stuff, subtract 1 from the power, and then multiply by the derivative of what's in the parentheses. Don't need to write that, but it's a times 1. Then we're going to plug 0 in for all of those x's. First two we did already. F of 0 is 1. F prime of 0 is still a half. Then we're going to plug 0 in for f double prime. So right there. So that means the parentheses is 0. The parentheses is 1. 1 to the negative 3/2 is 1. 1 to anything is 1 times the negative 1/4. So negative 1/4 is our answer here. Okay, but on the right side of this picture is where things change. We're going to start with ax squared plus bx plus c, which is a generic quadratic equation, or quadratic expression, or quadratic function, I should say. And now you can see why in the demo we used ax plus b instead of mx plus b, just so that we could continue using a, b, c in that order, starting with the highest power of x. So let's go ahead and do a q prime here. The 2 comes down. The a is a constant multiplier, so it stays. Copy the x, subtract 1 from the power, plus the derivative of bx is just b, and then plus the derivative of c is nothing. And then for q double prime, the derivative of 2ax is 2a, that's the coefficient of x, and then the derivative of plus b is nothing. And now we're going to plug 0 into each of these things. So when I plug 0 in for, right in here, q of 0, we get a times 0 squared plus b times 0 plus c. That's just c. Then we're going to plug 0 in here to find q prime of 0. So I get 2a times 0 plus b. That's b. Don't be fooled. The pattern is not just CBA. If you plug 0 in here, q double prime of 0, well, there are no x's to plug 0 into. Q double prime is always 2a. So q double prime of 0 is 2a. In fact, q double prime of anything is 2a. Okay, and now we are going to equate the things in the 2 middle columns. So let's write our 3 equations right down here. So 1 is supposed to equal c, and 1/2 is supposed to equal b, and a negative 1/4 is supposed to equal 2a. And again, typically you would have algebra to do to solve these equations, but the first two are trivial. They're already solved for a single letter. So all we need to do is solve this one for a. So we divide both sides by 2. And we get a is -1/8. Make sure that for each of these things, your final answer is the function, not just the values of a, b, and c. And so our function, remember, was up here. It says q of x. And so we're going to recopy that, but we're going to plug in the values of a, b, and c that we just found. So in our case, q of x equals a, -1/8, x squared, plus b, 1/2, x, plus c, 1. So that's our quadratic approximation for the same square root of 1 plus x function. Okay, number 5 asks us to fill in the table again. I went ahead and copied these numbers that we already calculated in the demo. But now we're going to plug in the same x values as before, these ones here, into our brand new quadratic approximation function, which is right there. That's what we just got on the previous page. So we are going to use a calculator here to help us, but the fact is plugging these numbers into this quadratic is not too terrible without a calculator. So for example, like the worst one, I guess, is a 0.04, right? So if I had to do q of 0.04 by hand, it would just mean -1/8 times 0.04 squared plus 1/2 times 0.04 plus 1. And none of these things is particularly terrible. -1/8, 0.04 squared is, let's see, so I guess it's 4 squared would be 16, but I need 4 digits after the decimal point, so it's 0.0016, and then half of 0.04, that's easy, 0.02, and then plus 1, and then to do an eighth of 0.0016, it's not bad, right? 8 goes into 16 twice, so I don't know, do I have this right? Is it just -0.002? Something like that, right? 1, 2, wait, is it one more 0? One more 0, silly. So it's that. And even if the numbers didn't go in nicely like they are here, it still wouldn't be terrible to do these ones by hand. But still, just to save a little bit of time, we're going to turn these things through in our calculator. So we'll type in our function right here, -1/8 x squared plus 1/2 x plus 1. Okay, I think that's good. And then we quit. And then we go, no, we'll do the table. Change it to ask. And then we'll just ask for these 3 numbers here, 3 and 0.3 and 0.04. Okay, so here are our approximate answers. Well, I guess these are our exact answers from the quadratic. So I'll type them or I'll write them here in our column. So 1.375 is the first one. And then 1.1388. And that was actually 875. I thought that was rounded. And then I don't think the last one is rounded. I think it's exactly 1.0198. And so now we're comparing, like the correct answers in this first column to our approximations using a quadratic, a parabola. Okay, so 2 compared to 1.375, well, that's not very good. How about 1.14 and 1.13875? That's quite good. We're only off by about 1/10,100,000th, only off by about 1,000th. And then 1.0198 and 1.0198, we agree to the 10,000ths place just for kicks. Let's bring that number back up. So so the square root of 1.0104 is this 1.019803. And so that is darn close to our approximation here, the bottom green number, 1.0198. So our parabola is approximating really well, clearly better than the line in most cases there. Okay, so here are the graphs of our 3 functions now. It says given approximate interval for where the quadratic function is, quote, good, and then is it bigger than the one that we gave in question 3? Okay, so where does the parabola, so that's kind of not the dotted one, but the one that's dashed and dotted, not the dashed one, but the dashed and dotted one is our parabola, the curvy one. So where does that look like it separates from the square root function, the solid one here? So I'll say maybe like right around here is where they start to separate, like maybe right there. I can still see the dashes of the tangent line at that spot, but I can't see the dashed and dotted parabola. And then on the right-hand side, looks like I can start to see maybe around here is where the parabola begins to show as being different from the square root function. So how about like negative 0.5 to 0.6, something like that? And so of course that's going to be a bigger interval than the one we wrote in question 3 because the parabola is hugging the square root function for longer. It's just a better approximation. It's a more complex function, and so it's doing a better job of approximating the square root function. Use your quadratic to approximate the square root of 2. So remember, we're still plugging 1 in for x just like we did in the demo. And so if we come back in here into our table, and we just ask for the value at 1, 1.375. So Q of 1 is equal to 1.375, which is pretty close to the 1.414, which is pretty close to the square root of 2. And I think this is a better approximation than the 1.5 that we got from the tangent line. What could you do if you needed an even bigger interval for which the approximation is good? So you just go to a higher degree, right? First one we did was linear, and that was pretty good in some respects. And then we did a quadratic, and that was better. It hugged the curve for longer. And if we did a cubic, it would hug the curve for even longer. And in the GeoGebra example from the demo for today, you saw a 49th degree polynomial did a really good job of impersonating the sine function. Okay, so you can read number 9. You can also read number 10. Moving on to 11. So linear approximation here, we'll go through the same steps as we did before. This one just doesn't have the blanks set up for us. So we start with sine of x. And then we have cosine of x. And then we're going to plug 0 in. It's not always 0, but in our examples so far it has been. So f of 0 is sine of 0, which is 0, and then f prime of 0 is cosine of 0, which is 1. And then we start over on the right-hand side here. This one asks for a linear approximation, and when we see that phrase, we always start with ax plus b. Its derivative is simply a. And then we're gonna plug 0 in to both of these new functions. So plug 0 in for x in the L function, we just get b, and plug 0 in to L prime, and you just get a. And then we make these two middle columns equal each other. And so we get 0 equals b, and 1 equals a. Remember, your final answer is not those. Your final answer is rewriting the function that you invented. So ax plus b becomes 1x plus 0. Or simply L of x equals x. So what does that mean? It means that near x equals 0, the sine curve is approximated pretty well by just the 45 degree line y equals x. So on the calculator, it says we're going to find these sine values. Again, make sure you're in radian mode. So here we go. I'll just do this one on the home screen. So the first one is sine of 0.5. Now, before I type this in, I'm just going to say that our approximating function is this. And so how much is L of the same 0.5? Well, L of 0.5 is 0.5. So I'm really hoping that if this is indeed a good approximation, then sine of 0.5 should be pretty close to the 0.5 that we got right out here as the output of this function. So is this close to 0.5? 0.479, that's pretty close. All right, how about sine of 0.02? So again, L of 0.02 is just 0.02. So maybe the final answer here is going to be near 0.02. That, I would say, is near 0.02. And then finally, what if we pick something negative, but still close to 0? So what would the answer be if you plug negative 0.007 here? It would be negative 0.007. So we're hoping this is something near negative 0.007. Indeed, that is quite near negative 0.007. And imagine if you had to find these sine values here and you didn't have a calculator in your hand, what would you do? How would you do it? In fact, you might even ask, what is the calculator doing when I ask for the sine of negative 0.007? Okay, 13. Quadratic approximation here for cosine near x equals 0. So we start just like before. Calculate a derivative. Careful with the fact that this is negative and not positive, but this is a quadratic approximation, which means we need two derivatives. Again, careful with your signs. Derivative here is negative cosine. We're going to plug 0 in to all three. Cosine of 0 is 1, sine of 0 is 0, with a negative in the front is fine. And then negative cosine of 0 is negative 1. Okay, and then we start all over here with, we'll call this one q of x. And because it's a quadratic, we always start with ax squared plus bx plus c. Take two derivatives, 2ax plus b. And this is just 2a. And then we're going to plug 0, the same 0, into all three of these functions. Okay, so q of 0 is just c, q prime of 0 is b, q double prime of anything is 2a. And then we'll write our three equations from those two columns in the middle. 1 equals c, 0 equals b, negative 1 equals 2a. So that means that a is negative 1/2. And so then our final answer here is that q of x is equal to ax squared, negative 1/2 x squared, plus bx, I'll write it even though we don't need it, plus c. And now I won't write it, negative 1/2 x squared plus. And then finally, we'll use this to estimate cosine of pi over 12. Cosine of pi over 12 is hopefully close to q of pi over 12. And q of pi over 12 is just negative 1/2 pi over 12 squared plus 1. And you can evaluate that in terms of pi. It's not hard, but given that we want a decimal at the end of the day anyway, I'm just going to write this on the calculator. So negative 1/2 pi over 12 squared plus 1. So that's our approximation. And what are we approximating? We're approximating cosine of pi over 12. Let's see how we did. Cosine of pi over 12. Again, it's trivial because I have this device in my hand. But if I didn't have this device in my hand, this would be a very hard problem, hard thing to approximate. Okay, so our approximation is up here, 0.9657. The right answer is 0.9659. Tenths, hundredths, thousandths, off by 2 10,000ths, just over 2 10,000ths. Just under 2 10,000ths is how much we're off by. Pretty close. All right, so we'll write our approximate answer here as 0.9657.